In this video, we'll continue our discussion of section 11.5. I'm going to do an example of finding the intersection of two lines. So I'm given two lines, line 1 and line 2. These are in the parametric equation instead of symmetric like the last problem, last example. So if I have two lines, the first two things I should find, or the first thing I should try to determine, let's just determine if they're parallel. So I take V1. All right, remember V1 comes from the numbers in front of our t, like mx plus b, so it's the slope. So -3, 4, and 2. There's my directional vector for V1. And then I check V2, and I write down those directional vectors, 3, 2, -1. And just like that last video, remember we talk about, I look here and I just like, okay, I multiply by -1. That's not what happens there. Okay, so we know that they are not parallel. There is no number I can multiply by 1 and get the other. If I could spell parallel right. All right. So they're not parallel. We know that. Now, I want you to ask, and we'll answer this in a minute. If they are not parallel, does that mean they have to intersect? We're used to in 2 dimensions, right? If they're not parallel, then of course they have to intersect at some point, but we're not in 2 dimensions anymore. We're talking about 3 dimensions. So in your head, what you need to be processing right now as we work through this, is there any way to have 2 lines where they don't intersect at all in 3 space? Okay, so the next thing we're going to do, once we determine if they're parallel, is we're going to check to see if they intersect. So check for intersection. So what we're trying to find is some kind of T 1 or 2, T1 and 2, such that when I plug them in, I get the same point on both lines. Like I would pick a T1, I'd plug it in here, it would give me some kind of XYZ, then I would plug another T2 in there, and we're wanting them to be the same XYZ. So it makes sense that if I want to check, I would take my x's and set them equal to each other. I would take my y's and set them equal to each other, and then I would also take my z's and set them equal to each other. So I'm going to do that here. Okay, so I got 1 minus 3t1 equals 1 plus 3t2. All the 1's and 2's are important. They're just labels. Don't let them trip you up. It's not a 1 or a square. It's the first t and the second t. Then I do my y's. I got 1 plus 4t1 equals 4 plus 2t2. And then the z's, 4 plus 2t1 equals 1 minus 2t2. Now, we have a system of equations back from algebra, and we're trying to solve when would t1 and t2 be good. So we have 3 equations, 2 unknowns. I only need 2, so I'm going to use this first one. So I'm going to write that down because I'm not going to change anything. The second one, though, I would really like one of these variables to go away. So what I'm going to do is I'm going to multiply both sides of that equation by 3. So I get 12 plus 6t equals 3 minus 3t squared, and we add down. So why I did this is now if I just add down, and I can do this with the equation as long as I add both sides up, I got 13 plus 3t1, and then notice on this side the t2's go away. The reason we did that, multiplied and everything, is now I can actually solve for t1. So I would minus 13. So minusing 13 from that, what is that? -9 divided by 3 is a -3. So we get t1 is -3. I plug that back into one of my equations. And now I use this to solve for t2. So we get, that's on the left side is a 10. Solving then for t2, I minus 1, I get 9. Divided by 3 is, sorry for my dog barking, if you can even hear it. T1 is that, T2 is that. What we are checking now, this isn't an answer. This just says, hey, the x and the z are the same when I have this, right? I have that the x and the z are the exact same thing. So it makes sense now that we must check the remaining. So check, I'll write a note here, check T1 and T2 in remaining in remaining equation. All right, so I plug it in. If it works out, then they intersect at those times. If they don't, then they don't intersect. We'll talk about that. So checking that, I got T1 is -3. I got T2 is 3. I plug it in 1 plus 4 times T1. And we're wondering, is that going to be the same as 4 plus 2 times T2? Well, I got -11 does not equal, that's 10. All right, so what that tells me is we have a new definition here. Maybe you've heard of it or not. So, one, they're not parallel. So, we don't have that. We checked for an intersection, and because we can make it where the x and z's are the same, but we can't make it where the y's are the same, we just showed that. That means that the lines do not intersect. And I know that's weird because you may be asking yourself, well, doesn't that mean that they're parallel? No, not exactly. Parallel in 3 space means they are running the same direction. So what that means, implies that these are skew lines. What skew lines are lines in 3 dimensions that do not intersect, but they're not parallel. Think about maybe 2 lines. One line, okay, so we have our axes. And consider the line, we'll call this the z-axis, that's one line. So let's say there's a line running up and down. And then I also have a line running like straight with the y-axis way out here. Not up, but like right here on this green line. So one would be running straight up and down, one would be running horizontal. They don't intersect, but they are not parallel because they don't run in the same direction. So these are what are called skew lines. So when showing 2 lines intersect, we would check parallel. And if they're parallel, then we stop. They don't intersect. Once we determine they're not parallel, we check for intersection by setting all our x's and y's equal. We solve then for using only 2 equations. We solve for T1 and T2. Then we have to, that only solved in this case for x and z. So we had to check for y in the remaining. So that's what we did down here is we checked to see, hey, would that work for the y component as well? It does not work for the y component. Since it doesn't work, that tells me the lines are skew. If it did work, then we would plug T1 and T2 into one of my lines and find the point of intersection.